This is my lab 6. So the purpose of this lab is to investigate the magnetic induction of eddy currents by analyzing how a falling bar magnet interacts with an aluminum tube and comparing the results to a computational model. In our results, the experiment time is falling around 1.25 seconds, and in a computational model, it was 0.973 seconds. So here are some of the fundamental physical principles. The Bussevart law, which describes the magnetic field generated by a constant electric current. We have Faraday's law, which is described when the magnetic flux or magnetic field changes with time, and the electromotive force is produced. And we also have Newton's second and third law, where F is equal to the mass times acceleration. For every action, there's an equal and opposite reaction. So in our observed model, here are the initial conditions of the bar magnet and the stopwatch. The system is a bar magnet, and the tube in the surroundings is everything else. And here is a picture of the setup and a diagram for each part. So our data, the magnet is 0.026 kilograms, and the mu of the magnet is 1.4778 amps times meters squared, and that's from our previous lab. The tube, 0.3 meters in length, and the width is 0.0065, the inner radius is 0.24, and the outer radius is 0.0305. So we did 3 trials with an average of all of those, and it was about 1.2 seconds of the falling magnet. So here's the computational model, and here's the initial conditions, which are just defining the constants that we have. And I also have geometry of the tube defined in the geometry, or like the mass. And you have a magnet defined as well. This is just the code for creating the tube. We also have an initial velocity set at 0, like t equals 0. So here's the rest of the code. You can see the law being applied. And here's the equation. We also have the calculation of magnetic flux and the calculation of forces, which is the magnet or the magnitude of the forces, and the force on the ring and the force on the magnet, and the gravitational force. So here are the results. We get the plot, velocity versus time, and we can see that velocity initially rapidly increases the magnitude, then it starts to plateau in the middle, and towards the end starts increasing magnitude again. And we, from the computational model, can see that the time of the tube is less than what was found in the observations in the experiment. In the computational model, it was 0.973 seconds, so some similarities and differences. Obviously, the times are different. The experiment was longer in the computational time. And assumptions we made, that was for the bar magnet as a magnetic dipole to the law. And we also neglect air resistance. And the way we also say the experimental model, the only forces involved are magnetic and gravitational, which is the same for the computational, but the experimental model is not necessarily true, which we'll discuss in the air portion. So possibly sources of air other than devices, or there are other devices and electronic magnetic devices in the surroundings that could have affected the forces. We're also neglecting the friction, and that may have happened against the side of the tube. So that may have caused like a longer time than what was expected, and the stopwatch when we were taking the time was inconsistent. Like starting and ending, that's based on human error and our reaction time not being super consistent. So how would the dynamics of the falling magnet change? Due to Ohm's law, the induced current in the tube would be much greater, and this would cause a magnetic force on the magnet and would counteract the gravitational force, preventing the magnet from falling. So what if there were holes and slots cut into the tube? That would affect the ring currents in the model. So the induced current in the aluminum tube would be less, since the holes would disrupt that current, and the magnet would probably fall much faster at the force not as strong to counteract the gravitational force.